Welcome to Typhoon HIL tutorial. In this tutorial we will be using example model which is included in Typhoon HIL Control Center Power Electronics library and demonstrating thermal model which is going to be coupled with electrical model. By the end of this tutorial, you will be able to understand the importance of using thermal models together with our electrical models in order to increase fidelity of our electrical system. Here with me is our engineer Ognjen, who is going to present this example and walk you step by step through its configuration and application. So Ognjen, can you give us more information on what you are going to talk about today?
We're going to talk about how to increase the fidelity of our models, of our electrical models, by adding some thermal models running in parallel to them, and not only running in parallel but actually being coupled with them and affecting their behavior. This is important to demonstrate the real impact the temperatures have in real life applications, especially where there's some power electronics in for example, outdoor applications. This is especially important. We have one such specific examples to show among our installation examples, which is located in the power electronics folder. So if you go to examples, models, power electronics, there's this induction motor losses calculation and thermal model folder. This is just to show you where it is. I actually have it already open here. Also, I did a compilation for our convenience, so the model is already compiled. So what we have here is first the electrical model. We have the power electronics model and the machine model. So what this application is, it's an induction motor being driven by power electronics drive, consisting of a rectifier connected here at the grid side. So we have the grid, the grid impedance, and then the rectifier itself, the DC link. Then we have this chopper here with its own control. So this is to protect the DC link. And the inverter itself, if we look inside, here it is. Then we have some measurement blocks, and finally we have the our motor, which is in fact the induction machine with squirrel cage. What's going to be specific in this model is that we are using the so-called voltage behind reactance model. So in our library there are current source models for machines mostly, but we also have a few voltage behind reactance models, and we intend to grow this type of models as they are more numerically stable and more numerically accurate. If you look at this machine, you will notice, at least our existing users will notice, that there is no snubber section. That's because we don't need it. Another thing that will be curious for users is the speed-based load control. So we are loading the model with we're loading the machine with the speed reference, and there is also the mechanical part, which is implemented in signal processing. On the other hand, we have the inverter control, which is also implemented in signal processing, and it's closed loop control based on the RPMs of the motor. Now the thermal models, this is our topic. So we have the inverter thermal model and the machine thermal model. You can notice that in both instances we are using ambient temperature to feed into the models, and as we will show later, that's actually going to be an important factor in the behavior of our electrical systems, both the inverter and the machine. The inverter thermal model is based on the Foster thermal model, which is typical for the IGBT calculation of the junction temperatures of the switches. And we can see that it's fully implemented in signal processing. So the vector of the junction temperatures of each switch, and we have 6 of them, is taken to feed the inverter, and this actually allows us to feed the junction temperatures into the inverter model, which in our case of 3-phase inverter has enabled losses, and that's exactly what enables us to eventually come to the temperature values, because we are actually modeling the switching losses and then coming around to get the temperature back in. So this is how we close the loop between the thermal model done in signal processing with the electrical model of the inverter. On the other side, we have the machine thermal model, which is taking in the stator currents, which are measured in this block inside. So there they are. And these are also the inverter output currents. The machine thermal model is also taking in the ambient temperature, and it gives us then the motor temperature here, and also the difference in delta, the difference in resistances as delta R. Now, delta R is actually the changing of the stator resistance on the terminals. And we've done a smart way to kind of couple this thermal model with the electrical model of the machine by utilizing these variable resistors. So it's a very useful component to have, and alongside of them we also have variable capacitors and inductors in our library. The only thing what users should take note of is that when you have variable components, you need to make sure that the hardware configuration actually supports variable passive elements. So what I've done here is just basically open the schematic settings. You can either access by F12 or by going to model section, then schematic settings. I have selected HIL 402 with configuration 4, which is the configuration that allows me to do time varying elements. And the time varying elements is actually the name of the resource we are using on FPGA when we have variable passive elements in our model. And of course configuration 3 also has that, but I'm using configuration 4 because I need machine solver as well. So make sure you select proper configurations when working with variable passive elements. Okay, what else could be said about the model? Pretty much, that's pretty much it. Other things that could be commented really exist in some examples are kind of repetitive. I already compiled the model, so we can just go to SCADA and play with it and see how actually these models of thermal and electrical models, how they work together. We will start the simulation. What we have here is a custom design interface to allow us to play with this model, to provide stimulus and observe the results. You'll see some normal things that you will meet throughout our models, which are kind of the the ability to play with the grid side, which is not so much of the interest today. Also, you could test the DC link protection here. What we want to see is the temperatures, really. So we have the observation of IGBT junction temperatures, which are kind of settling in compared to the rising, as they were rising when we started the model, and then reaching some more stable operational value. By 1 minute of simulation, we will see that they're about 68 degrees Celsius, and also the motor temperature by this time is about 30 degrees, and the stator resistance 2.9. We have the maximum speed of the motor, and the load is at 60 Newton meters. The inverter efficiency by this time is 0.97. So take note what happens when we play with ambient temperature. So let's say I increase this temperature to 40 degrees. This will immediately have an impact on the IGBT temperature here, and we can see that it jumped to 95, and the motor temperature is about 46. The stator resistance increased as well, so just to show that the resistance is affected by temperature. The inverter efficiency is still unaffected, but if we were to go, let's say, just 50 or more, we can try. That's already bringing the efficiency to 0.96. So something to think about: if this was an outdoor application, the inverter efficiency is not only affected by load, but by temperature as well. And speaking of load, so here we can see, for example, how the inverter output currents look like while the load is at 16 Newton meters, and I could, let's say, cut that in half, and you can see that now my inverter efficiency has went down even lower. So the inverters generally don't like working in the low load condition, and as you can see, if we look back the scope, the currents are kind of more distorted than before. So just to demonstrate that again, we go to 16, it's somewhat better signal than 8. So that's on one hand, but at the same time that allowed certain cool down of the inverter and the motor as well.
Thank you, Ognin, for this brief description and detailed explanation of this model. Dear listener, thank you for your attention, and we hope that this tutorial will be useful for you and help in working with thermal model.